So welcome back to another day of calculus. The learning objectives today, it's roughly section 2.4 in your book. We will be talking about continuity. In particular, we'll be talking about what's the definition of continuity, what is left continuity, right continuity. We'll be talking about what does it mean to be discontinuous and three basic types of discontinuities. We'll show examples of continuous functions, and then time permitting, we'll show some homework exercises or some section exercises. Okay. I also have a video series on continuity. I'll post the links on the Google Classroom. You can also find them in the playlist that I posted. If you click on the link for my calculus series, then you can scroll down and find the continuity videos there. They're similar to what we do in class, but not the same. Class, sure, I'll be re-explaining concepts, but also answering your questions and doing problems. Like my general calculus video series has higher production values and is there for you anytime you want a refresher. So are there any questions before we begin? So thank you for turning in your homework. I've just begun grading, not very far along, but I'll try to finish that up soon and give you good feedback. So today has lots of terminology, so I'll introduce you to the terminology, to what the words mean, but you will have to do some memorization and some practice to get used to it. So to start us off, try to get this wire in my microphone a little out of the way. So we've been talking about limits in the past. We've been talking about what's the limit of a function. We've been talking about left-hand limits and right-hand limits. So I'll draw you a schematic picture of a function . So here's an example of a function. Let's say this is the graph of y equals f of x. And if I want to calculate, check, can we see that? I'm not standing in the way too much. Yeah, if we want to calculate the limit, say, of f of x as x goes to a, think about what that's going to be. Put your answer in the chat. What's going to be the limit of f of x as x goes to a? Give you 10 more seconds if you want to participate. Put that answer in the chat. What's going to be the limit of f of x as x goes to a? Getting some answers coming in. Okay, yeah, so I'm hearing that maybe the answer is 2, and I agree with that. So you can see like the y value here is 2, and as x is getting close to a, the y values seem to be approaching the number 2. On the other hand, you can ask yourself, what's the value of the function f at the point A? The value of the function f at the point A is equal to 3. That's what we mean by filling in that point. So this is an example of a function that is discontinuous at a point x equals A. And let me actually write down what is the definition of continuity. So a function f is continuous at a point A if the limit as x goes to A of f of x is actually equal to f of A. So a function f is continuous at the point x equals A if the limit as x goes to A of f of x is actually equal to f of A. So this, therefore, is an example of a function that looks continuous at every single point except the given point x equals A, because the limit of the function as x goes to A being 2 is not equal to the value of the function at that point. And you could just say that f is continuous on an interval, say on an interval from A to B, if it is continuous. Try not to stand in front of the board too much. If it is continuous at every x in the interval. So for instance, this function, this schematically drawn function, if I take the interval from maybe call this 1 and call that 2, this function appears to be continuous on the interval from 1 to 2, because if I look at the graph over that point, it appears that at every point the limit as x goes to whatever point you're looking at will be equal to f of x. This x equals A appears to be the only point where the limit of f as x goes to A is not equal to f of x, because you have this upwards jump. Let me pause. Any questions about that definition? You can put them in the chat or yell them out. Okay, so I'll move on to another concept. So similar to the idea of being continuous, let me draw you another schematic picture. So let's take a function that does something like this. So try to draw it with some reasonable accuracy. So this is a function that f of 2 is equal to 2. And this is a function that appears like it is not continuous at the point x equals 2, but it appears that it is continuous at every other point. Why is it not continuous here? Because you look at the limit as x approaches 2, and the limit is not equal to f of 2. The limit is not equal to 2. In fact, the limit doesn't exist, because as x gets close to 2, the y values will switch from being close to 2 and being close to 4. And the limit can only exist if, when x is close to a specific number, all of the y values, not just 1 or 2, have to be close to whatever the limit is. So since the limit as x goes to 2 of this function does not exist, this function is not continuous at x equals 2. So in this picture, f is not, sometimes you'll see me abbreviate continuous by CTS. So f is not continuous at x equals 2. But there are some positive things that we can say about it. So first of all, I can notice that, remember last time we discussed left and right limits? So even though the limit doesn't exist, both the left and the right limits do exist. So if I take the limit as x goes to 2 from the left of f of x, and if I take the limit as x goes to 2 from the right of f of x, remember this notation, this negative in the superscript means that we're only considering x values that are to the left or less than 2 when we're thinking about what do the y values approach. The plus in the superscript means that we're only considering x values to the right of the number 2 when we're considering those y values to determine whether or not there's a limit. So both of these limits do exist. And please put your answer in the chat. What are the two limits? What are the two left and right hand limits? Give you maybe 10 more seconds, but by visually inspecting the graph, please tell me what's your guess for the left and right hand limits. Seeing some answers, thank you, and a couple more seconds. So now I'll go through it. So for left-hand limit, we want to consider only those values of x that are to the left of the number 2. So these values. So as the x values are approaching 2, think of the y values. Where are they approaching? X values approach 2 from the left, y values approach 2 from the left. So I'm seeing the left-hand limit being 2. And what about the right-hand limit? When we're approaching the x values just from the right, from those numbers bigger than 2, what are the y values doing? The y values are approaching, looks like the number 1, 2, 3, 4. So I'm seeing left-hand limit equals 2. I'm seeing right-hand limit equals 4. And whenever you have the left-hand limit and right-hand limits disagreeing, that means the limit doesn't exist. So just like a little note about that, the limit exists exactly when the left and right limits exist and are equal to each other, which is not the case here. But what about continuity? So definitely this function is not continuous at x equals 2, but there is something we can say about it, because remember that f of 2 It has a value, it's equal to 2. And so I'm noticing that the left-hand limit is equal to f of 2, while the right-hand limit is not equal to f of 2. So I'm noticing that the left-hand limit is equal to f of 2, while the right-hand limit is not equal to f of 2. And that gives me an idea for like a new definition. I'm going to say that the function is left continuous at x equals 2 if the limit from the left as x approaches 2 is equal to f of 2. So we can say that where can I write it? So we can say that f is left continuous at x equals a if the limit as x approaches a from the left of f of x is equal to f of a. And in our particular example, our schematic example, a was equal to 2. And the limit as x approached a from the left was equal to f of 2. Similarly, you would say that f is right continuous at x equals a if the limit as x approaches a from the right was equal to f of a. So in the schematic picture that I've drawn, you've got a function that is left continuous at x equals 2, but is not a right continuous at x equals 2, because the right-hand limit being equal to 4 is not equal to the value of the function. And the same way that a function has a limit at x equals a if and only if the left-hand and right-hand limits exist and are equal. A function f will be continuous at x equals a if and only if the left and right-hand limits exist and are the same. So this is a lot of terminology. Can I clarify or answer any questions around those definitions? We should speak a little bit about what's the number for x approaches. So in the middle of the board, it's x approaches 2 from the left, and the lower display is x approaches 2 from the right. At the very top of the board, it says f is left continuous at x equals a if the limit as x approaches a from the left is of f of x is equal to f of a. You're welcome to direct, you can and should direct message me questions. I'll try to answer them out loud because I think the answers benefit everybody, but without identifying who asked it if you ask me something directly. So hopefully that's okay. We should talk about the types of discontinuities that can happen and how to classify them. When you have a discontinuity where the left and right-hand limits are not the same, that's called a jump discontinuity, like this one. So this is called a jump discontinuity. And the reason why it's named that way makes sense because the graph looks like it's jumping upwards and then continuing on. Let me write that down. F has a jump discontinuity at x equals a if the left and right hand limits exist, but they don't match. So if these two limits exist, but are not equal to each other, and both limits exist. I'll say more about that parenthetical statement in a minute. But you can see why it's called jump discontinuity. It looks like the graph is jumping up. There's another kind of discontinuity. If you go back to this first picture that I drew, like you take something like that with now f of 2 equals 4. This was a discontinuity that we saw originally where the limit of f of x as x goes to 2 was equal to 2, but it was yeah, maybe losing the batteries on the sounds a little bit. So I'll try to keep an eye on that. So thank you for mentioning that. Definitely mention like any visual or audio issues as soon as you can, and I'm working hard to try to make them better. But what I'm going to have to do for today, I think, is what I'm going to have to do for today, I think, is just give up my lavalier and stay close to the computer and just use computer sound because the battery is died. So I apologize for that. So what I'm going to do is I'll run the whole rest of class out of the computer, and I think I'll do my examples on Desmos so that we can see them that way. And I may have to type some things into the chat instead of, well, I guess if I have to write, I'll probably write on the board so that you can still be able to see it when you go back and watch the lecture on YouTube. Okay, so but we've seen jump discontinuity and removable discontinuity. Why is this named removable discontinuity? It's because if you just filled in the hole there, the discontinuity would no longer exist. So because you can change the value of a single point of the function, and therefore remove the discontinuity. That's where the name removable discontinuity comes from. You think of just filling in the hole and you've got it. Whereas if you had a jump discontinuity, you can't just change one value of the function and fix it. Like you can't fix that jump. There is a third kind of discontinuity that we see often, and that's called an infinite discontinuity. You make up some example really quick. The infinite discontinuity you're probably like most familiar with is like if I just did y equals 1 over x. So let me show you that. Like if I just did y equals 1 over x on Desmos here. So this is a function that is continuous at every point except for 0. And I guess maybe I'll even do y equals absolute value of x to simplify the situation when we're first talking about it. So this is a function that's continuous at every point except 0, and I'll call this f of x. And I'll say that f of x has an infinite discontinuity at x equals 0. And the reason why it's infinite is because if I take the limit as x goes to 0, the y values are unbounded. The y values tend towards infinity. So 3 common types of discontinuities are removable. Let's see if I can make one up. So let's take like x squared minus 9 divided by x minus 3. So x squared minus 9 divided by x minus 3 looks like a straight line. Why is that? That's because x squared minus 9 factors as x minus 3 times x plus 3, and you can think of the x minus 3's canceling as long as x is not equal to 3. However, when x is equal to 3, can I zoom in? I better know. Oh, there it is. So why can't I zoom in? There we go. But when x is equal to 3, the y value is going to be undefined. Let's see if we can get that from the software. Yeah, there it is. Desmos doesn't like to draw those circles, but you can see when x is equal to 3, it's undefined because you can't divide by 0. So this green function is an example of a removable discontinuity, because if you made a new function g and just defined it to be equal to just defined it to be equal to 6 when x is equal to 3, that would fill in the discontinuity. That's why it's called removable. And finally, the third type that we saw was jump discontinuity, and you can look at something like, you see me type in floor, that's the floor function. Floor means the greatest integer that's less than or equal to the value. So in this case, it's the greatest integer that's less than or equal to 2 times x. And you can see that there's a discontinuity now at there's a discontinuity at 1/2 where it jumps up. There's another jump discontinuity at 1. There's another jump discontinuity at 1.5. So you're seeing these are like maybe like left continuous, but then they have jump discontinuities at each regular intervals of 1/2. Just to give you a good visual picture, that's what jump discontinuities look like. That's what removable discontinuities look like, even though you can't really see in the picture that the 3 is removed. And this is what infinite discontinuities look like. That's the case where you have the limit running off to infinity as x goes to 0. Now, if I just did like 1 over x, then this would be like an infinite discontinuity from the right and an infinite discontinuity from the left. Strictly speaking, the limit of 1 over x doesn't go to infinity as x goes to 0 because some of the y values are going to positive infinity, some are going to negative infinity. That's why I put that absolute value there. So this one definitely has like a single infinite discontinuity at x equals 0. And let me pause for questions. Any questions? Okay, so those are 3 types of discontinuities. But that's not to say that all discontinuities are of those 3 types. There are other kinds of discontinuities that don't have a classification. And so let me show you an example of a discontinuity that is neither removable nor infinite, nor a jump discontinuity. So let's look at something like the classic example of this. Start with sine of x. So there's the graph of sine of x. Then do something like sine of 1 over x. And can zoom in. Zoom in. It looks like, it almost looked like it's fully colored in, but like what's happening is when you do sine of 1 over x, all those oscillations, they're kind of compressed. Like if you look at sine of x, it's a periodic function, it has these waves. When you do 1 over x, you're compressing all of those waves into the space from like negative 1 to 1. You can see that here. And as you get closer and closer to 0, you just wildly oscillate back and forth. So this function is not defined at 0. Not defined at x equals 0. You can see that you can't plug in x equals 0 and get an answer. Not only is it not defined at x equals 0, but it's not continuous. And you cannot fill in a single value, so you cannot remove the discontinuity. You can define the function at 0 to be any value it wants, but because it oscillates so quickly, it'll never be approaching a single value. It's definitely not infinite because it's not going to infinity. It's definitely not a jump discontinuity because those right and left-hand limits don't exist. So this is a kind of discontinuity that doesn't follow any of the 3 classifications that we know. So there's lots of ways that a function can be discontinuous. On the other hand, the good news is that this function is continuous at every point except for 0. All of the trig functions are continuous on their domains. So like if I look at cosine of x, that's continuous. If I look at tangent of x, I mean, it's continuous on its domain, right? Like where you see these like vertical asymptotes, those occur at, the first ones occur at pi over 2 and negative pi over 2. And then it's periodic, so they continue to occur at regular intervals. So tangent is continuous except at pi over 2, negative pi over 2, and then like plus or minus 2 pi, you know, like 2 pi plus pi over 2, 4 pi plus pi over 2. It's discontinuous there. 2 pi plus negative pi over 2, 4 pi plus negative pi over 2. Continue to be discontinuous. But let's just focus on like pi over 2. So if you take like the limit as x goes to pi over 2, then what's happening? The y values are approaching infinity. So tangent of x has an infinite discontinuity at x equals pi over 2. Of course, pi over 2 is not in the domain of tangent of x. That's why I say tangent is continuous on its domain. Stop sharing for a moment. Let you ask any questions. So just a few basic facts about continuous functions. These are facts that you prove in a course on real analysis, like in Math 312. But here, I'll just state them for now and we can come back to them. And I'll do this with Notepad, and I can then go into Desmos if I want to draw some graphs. But so how to make new continuous functions, old ones. So what can you do? Like if you have two functions that are continuous, you have two functions that are known to be continuous, then their sum is also going to be continuous. And so, like, why might that be true? If you go back to the definition, like, you're continuous if limit, you're continuous at a if the limit as x goes to a of f of x is equal to f of a. So if f of x and g of x are known to be continuous, then you know, like your assumption is that limit, like for any a, limit of f of x as x goes to a is f of a, limit of g of x as x goes to a is g of a. And then I'm asserting to you that the sum is going to be continuous. In other words, I'm asserting to you that limit as x goes to a, f of x plus g of x is supposed to be f of a plus g of a. And the reason why you know this is true is actually because of the limit laws. So the limit law says that if you take the limit of a sum, then it's equal to the sum of the limits. And the sum of the limits in this case are limit x goes to a f of x, which you know is equal to f of a, and limit x goes to a of g of x, which you know is equal to. So really, the limit laws and the rules of continuity are basically the same thing. So in a similar manner, like if you have two functions, f of x and g of x are known to be continuous, then f of x times g of x is continuous because of the product limit law, because the product of the limit is the limit of the products. Similarly, like if you have f and g of x are known to be continuous, then the fraction of x over g of x will be continuous so long as g of x is not equal to 0, because you can't divide by 0. And this also showed up in the limit law too. The limit law said that the limit of a quotient was equal to the quotient of the limits so long as the denominator was not equal to 0. So then recognizing that the definition of continuity just means the limit is equal to like f of a, you can transform those limit laws into statements about how to make new continuous functions from old one. Namely, you can multiply a function by a constant, stays continuous, add continuous functions together, sum will be continuous. You can multiply continuous functions together and stay continuous. You can divide continuous functions, and the result will be continuous so long as the denominator is not 0. And why is this helpful? Because you can build up a list of functions known to be continuous. So, like for example, all polynomials, and so this follows from the limit laws. It's a good exercise to show that. And all 6 trig functions, so that's sine, cosine, tangent, cosecant, cotangent, secant, are continuous where they are defined. So like you saw that with tangent. It's not continuous at pi over 2, but it's also not defined there. Exponential and logarithmic function are continuous. And so like you can put all this together to make new continuous functions. That's what I'm saying. So let's give it a shot. So like if you look at let's go back to Desmos. Let's take f of x equals something like x squared plus 3x plus 2. So there's a polynomial for you, and I multiply it by sine of x. Let's zoom out to get a nice picture of it. Like, you might not be that familiar with this function, but at least you know that it's continuous because it's a product of 2 continuous functions. That is to say, it's a product of polynomial with trig function. Now, what if I took something like let's put that away. What if I took something like g of x equals sine x, now divided by that same polynomial? So where is this going to be continuous and where won't it be?
It'll be continuous everywhere except 0, right?
Yeah, right. So this will be discontinuous exactly at the places where the x squared plus 3x plus 2 has roots. And I expect to see like infinite discontinuities there, because when you're dividing by 0, I think the y values should blow up. And I think you're seeing that here, like perhaps. Like you're seeing, it's hard to visualize on the graph, but you're seeing a place where we're going off to negative infinity. And that's going to be telling you basically we've got a 0 of polynomial x squared plus 3x plus 2. You could use the quadratic formula to find them out exactly, but like somewhere around this line, which is kind of cool. And just like one more remark, it's kind of a throwaway remark in the book, but I mean, it's really useful. It's actually pretty hard to prove. This is theorem 4 in section 2.4, if you're following along, which basically says that that if you have a function given to you, and you know it's continuous, and if the function is invertible, then the inverse function will also be continuous. So if you've got a continuous function on the interval, then the inverse function is also continuous. It's actually pretty hard to prove, but it's true, and so you'll use that sometimes. Examples. The most famous example of that is, look at f of x equals e to the x. Now look at its inverse function. You can find the graph of an inverse function by reflecting over the line y equals x. You perform that reflection, try to visualize it in your head, and now here comes the inverse. It's g of x equals natural log. Inverse of e to the x is natural log. So long as e to the x is continuous, the natural log will also be continuous. With a caveat, right? So natural log is not continuous at 0. It's also not defined at 0. It's not continuous at 0. It's got that infinite discontinuity. So what's going on there? Have I just lied to you? Not exactly. The thing is, like when you take the inverse function, you swap the domain and range. So the domain of natural log is equal to the range of e to the x. The range of e to the x is open interval from 0 to infinity. Just those positive numbers. As you can see, e to the x never goes below 0. So the domain of natural log of x is also going to be the open interval from 0 to infinity. And since e to the x is continuous, its inverse function is also going to be continuous on the same interval. So e to the x is continuous and its range is 0 to infinity. So the inverse function natural log of x is going to be continuous on the domain 0 to infinity. So a little bit of yoga to get used to. When you take an inverse function, the domain and the range switch. But that's what that theorem 4 is saying. We won't use that heavily in this class. That's just for your reference, that, you know, so you can be knowing that inverse functions are also going to be continuous if their parent functions are continuous. So I'll pause for questions and comments. So I apologize, we didn't get to work any chapter exercises today, but we did get through a fair number of examples, and we did get through lots and lots of terminology. I try to work some more chapter exercises in to my lectures more often. We might try to flip the classroom some days where you watch video lecture first, and then in the classroom we do mostly problems. That could be another technique. But seeing no questions, I'll just tell you to have a great day, and I'll see you on Friday. Come see me in office hours on Thursday if you like. Take care.
Thank you. Bye.
See you.
Thank you. Bye.
Have a good one.